Alrighty, good morning, gang. Welcome back to pre-calculus. Let me flip on the document camera and get things moving. Kitty cat, you're gonna have to move, sweetie. Yeah, you're right where Daddy needs to teach. Okay, yes, it's time for you to move. Hey, big girl. Come on, come on. I know. You don't want to. Okay, come on over here. Okay. So, this, of course, is MAC 1140, section 008. A good black pen here somewhere. Which is pre-calc. And today is 8, is it 30? Oh, that's pushed out. Come on. Oh, looking good. All right. This is the 31st, right? Okay. So last week we talked about a handful of kind of preliminary bits. Today we're going to begin just talking about functions, which is section 2.1. We're going to talk about graphs of functions. Which is section 2.2. You do have another homework set up. I'm going to show that to you really quickly. The homework that I'm opening today is due Thursday at the start of class. So remember the way we do things, you're going to have 2 homework sets due every week. Last week is the only exception. So starting today, starting this week, you're going to have 2 homework sets. I'll release one on Tuesday. That will be due on Thursday, the following class. And then I'll release one on Thursday, which is due the following Tuesday at the start of class. And this is meant to just kind of keep you up to pace. WebAssign estimates that this homework set is going to take you about 2.5 hours. So make sure that you plan ahead and put time in for it. It's not especially short. There is plenty for you to do here. There's a handful of graphing problems. There's a lot to do with function notation. Most of it is just making tables or trying to understand piecewise functions. The sort of thing that you've no doubt done some of in the past, but we're going to be doing with slightly more complicated functions. You see a lot of focus here on things that look like this. These are called piecewise functions. We're going to talk about them quite a bit today. But before I get into the actual mathematics we're going to cover today, I want to talk a little bit about the sort of attitude, mentality that I want you to approach this particular homework set with. So you notice many of these questions ask you to graph a function. And I know technically we haven't talked about graphs, but I also know everybody here knows what a graph is. As you solve these homework problems, it is essential that you graph these things by hand and then match your graph to the one in WebAssign. I don't like for you guys to stress about, oh, this is my last attempt on this question or anything like that. So I don't set, a 3-attempt max on any of these. You guys can submit the homework problems as many times as you like. You can work them until you get them right. I know what that means. I know that means you can come in here and guess, oh, no, that's wrong, guess, oh, no, that's wrong, until you get it right. That's not going to teach you jack shit. I want to be really clear about that. Guessing until you get it right teaches you nothing. And on the exams, you're going to be required to graph functions like these by hand. If you practice that skill here in the homework, then when it comes time on the test, you'll be good at this and it will not feel hard at all. If you hack your way through the homework by guessing until you get the right of the 4 graphs WebAssign lets you pick from, then you're going to have a very hard time of this on the test. So please do yourself a favor. When you get down here to these problems, like the stuff that comes after number 18, make sure you draw the graph by hand and then match it to the one in WebAssign. Don't just try to guess which one is correct, because that's like shooting yourself in the foot. It's not doing any good. All right, so that's the new homework set. It's due Thursday. It's due Thursday at the start of class, at our next class. I heard a question there. Was that Megan? What's up?
On the other homework, on some of them, if you had like problems, you could either read the book or you could watch a video on it. Will that be like for the graphs and stuff too? Will that be for like continuous for all of the other homework assignments?
I think the majority of the problems have some sort of resource you can click to get help on that problem with. Maybe not every single one, but at least half of them do. And if there's a homework problem where you're not getting what you need, you can always come to office hours and talk about it. I've had a few people come by office hours. We've had good experiences there, been able to get the help they want. The other option is to post things to the Discord. So this is a really nice way to get help. It's my calc class, but you can post questions to the Discord, and some folks have been doing that. You'll get much faster answers there, obviously, than using something like the tutoring center or waiting for an email to come back from me. But yeah, certainly many of the questions will have those. I'm not like pulling those out. I'm not going to cut those off at some time. Those little like look at the ebook or watch a little video, those things will be consistent through the semester. And then also consider posting to the Discord or sending me a Canvas message, something like that, or come by office hours if you want help on a problem.
Okay, is Discord something that you have to download?
No, you can. There is an app. You can get an app. You can get an app on your phone. I think they might have a desktop app also, but I just use it in the browser. So you go to discord.com or discord.gg was the old URL, or just follow the link from the announcements here. And it's real simple. You don't have to put in any identifying information, no payment information, nothing like that. It just loads you into the chat.
All right, cool. Thank you.
Yeah, of course. Okay, so today we're talking about functions. It feels a little dry, but we have to do it. We need to define what a function is. So what is a function? Does anybody have an idea or a description of a function that kind of makes intuitive sense to them? I know we've all seen these before.
Would it be like a set of inputs and outputs that you get?
Yeah, that's it exactly. So a function is a rule for pairing inputs with outputs. Now, a rule like this in general would be called a relation. So not all rules for pairing inputs with outputs are necessarily functions. So a function is a rule for pairing inputs and outputs with the restriction that each input is paired with only one output. And the reason for that restriction is so we can kind of talk about the output for the function by talking about the function and a particular input. So when you see that notation f of x, what that means is the output from the function f when it's fed the input x. So kind of that one little bit of notation, f of x or f of 2 or f of 7, encodes all this information. It tells you what the function is, it tells you which input you're looking at, and then the object itself, f of 4, is the output you get when you feed the input 4 to the function f. So by saying every input has to go to one and only one output, we're able to kind of simplify the picture. If you have a rule for pairing, a relation, that's able to send one input to many different outputs, then just by referring to the input, I don't necessarily know which output you want to talk about. So this additional stipulation beyond the input-output pair, that every input goes to only one output, allows us to talk about them in a way that is just more efficient notation-wise. It also has some other utility that we'll see in a minute. Let's see. So the first place I want to go is just showing you the notation. So usually we'll use letters like F, G, and H for functions. And the notation, say f of x, describes the output from the function f when fed the input x. So one of the things that happens in high school math classes or earlier college math classes, you get used to f of x kind of being the function, but really f is the function. X is the input, and f of x, this thing, is what you get as the output when you feed the function f the input x. So you can kind of think of these parentheses as being like a mouth, and they're going to gobble up the input x, and they're going to poop out something else. All right, so think of this as kind of like an animal. It's got a mouth, it eats this stuff, and then it poops out this stuff. Let's get some practice. So let's compute f of 0, f of 2, f of -1/3, f of a squared, f of a plus h for the function f defined by f of x equals. How about?
Can you bring the camera down a little?
Yeah, here, let's do it like this.
Thank you.
1 over x squared plus 1. You have a handful of problems like this in your homework, and the big idea is just getting you comfy with the function notation. It might seem like a silly or trivial thing, but believe me when I say there will be questions and problems later on in the term where just being able to correctly understand what this means is valuable, is the majority of the problem. So let's get started. Oh.
What does that say? F of a plus h?
Yeah, this is
Okay.
f of, and then the inside there is a plus h.
Okay.
The basic idea when you want to compute these things, these are a bunch of different outputs, right, from this function down here, is that you're going to replace the variable x by whatever is inside the parens. And when you do that, you usually want to do it in parentheses. So you'll see me when I go plugging things in for x here, I'll be doing that in parentheses, and you really want to get in that habit yourself. I'm going to let this cat outside so she doesn't drive us crazy. Oh. Okay. So getting started here, f of 0 is what I get by looking at the formula for f of x and replacing the x by 0. You want to get in the habit of doing that with parentheses. Now here it doesn't matter because parentheses 0 squared is the same as 0 squared without parentheses, but for some of these other things, it is going to matter. So 0 squared is 0, 0 plus 1 is 1, so this is 1 over 1, which is just 1. So I'd say f sends the input 0 to the output 1. The other guys are going to go the same. F of 2 would be 1 over parentheses 2 squared plus 1. And we just write this down and then look, okay, what is parentheses 2 squared? Well, that's the same as 2 squared, that's 4. Okay, so this is 1 over 4 plus 1, which is 1/5. F of -1/3, this is a place we're going to have to grapple a little bit with some fractions. That's not too bad. This is 1 over -1/3 squared plus 1, like this. the square of -1/3. So this is a place where the parentheses really matters, right? If I wrote -1/3 squared without the parens, it's not clear whether the negative is being squared or isn't being squared. In this case, since I'm being careful and using my parentheses, you can see that the negative is definitely inside the parens. And so the negative should get squared along with the 1/3. So that's -1/3 times -1/3, which is +1/9. So downstairs here I have 1/9 plus 1. And then remember that fraction bars always imply some parentheses, right? As we simplify this, we want to be clear sort of what's the top of the big fraction and what's the bottom of the big fraction. To add 1/9 to 1, I think I need a common denominator. So I think of 1 as 9/9. So this is 1/9 plus 9/9, which is 10/9. And it's at this step where those big parens that I put on the outside are really useful. Because if you have 1 and then a fraction bar and then 10 and then a fraction bar and then a 9, without any parentheses, it's not clear kind of what gets flipped and what doesn't. But here it is clear. This is a big fraction. The big numerator is 1 and the big denominator is 10/9. So the 1 gets left alone and the 10/9 gets flipped. This is 1 times 9/10, or just 9/10. All right, these next few are a little more interesting. F of a squared. Come in here and swap the x for an a squared. So this is parentheses a squared squared plus 1. And remember our rules for exponents from last week. If you take a power and you raise it to another power, you multiply the powers. So a squared squared is a to the 2 times 2, or a to the 4. This is 1 over a to the 4 plus 1. And then the fun one, f of a plus h. And I have some questions. So don't write this down, just think along with me. Is this the same as f of a plus h? Is this the same as f of a plus f of h? Or is this something else? So this is what I mean when I talk about understanding function notation, being able to distinguish the meaning of these different sort of things. These are called functional equations, where you've got an equation relating two statements about a function in function notation. So how about this first guy? Is this correct?
No.
No, yeah, these are very different, right? F of a would be 1 over a squared plus 1. And if you add the h on the outside, that's very different than what you get if you add the h on the inside. What about the second one? Is this correct?
Neither. No.
Very good. Yeah, neither of these are correct. The second one can be tempting because it kind of looks like we're distributing the f. It looks like something that would be valid algebra-wise. But that's what I mean when I say we're talking about function notation. This is not f times the quantity a plus h. This is f of a plus h. So we can't distribute. It doesn't work like that. That's not what this notation means. Even though it looks like multiplication, it's not. This is the input we're feeding to the function f. There are some functions that do this, where you can take a function and then look at a sum inside and split it up. Those are called linear functions, and they're linear in a sense that's slightly different than graph having a straight line. But any function whose graph is a straight line and goes through the origin would satisfy this, but only those, right? So generally, neither of these are true. Something else is what we want here. And the something else, like we said earlier, is what you get when you just replace the x in here by a parentheses x plus h. So this is 1 over parentheses, a plus h squared plus 1. right? And you see without those parens, it's going to be hard to even understand what this means. If we had an a plus h squared without parentheses, like is the a being squared, is the h being squared? And then if we wanted to clean this up, we can do a little bit of work here. A plus h squared, remember this is a plus h times a plus h. So that would be a squared plus 2ah plus h squared. So here we would have 1 over a squared plus 2ah plus h squared plus 1. Sometimes when you're working with objects like this, you'll want to multiply out expressions like this. Sometimes you won't. And generally what you want to do is kind of think about what your goal is. Where are you trying to go? You're trying to cancel something, you're trying to factor something. By thinking about what your end game is, you can decide whether you want to leave something like this or multiply it out like this. Okay. So the way I've described this function for you in our example here is what's called an algebraic description of the function. I just give you a formula for the output in terms of the input. But that's not the only way to describe a function. There's lots of other ways we can convey what the rule is for a given function. One of those ways is algebraic. Another way is verbally, right? I can describe what a function does just in words. Like I can say the function f takes its input, multiplies by 3, then add 1, and that's it. You know, okay, well that would be a description of a function that we could translate into algebra. It might seem a little silly to do that, but later in the term when we talk about the inverse of a function, you'll see that having a verbal description of the original function can be really useful for cooking up the inverse of that function. When I use the word inverse, I mean something other than reciprocal, right? Not like flip it over. I mean undo. So different ways. To describe. First, we can do it algebraically. You know, like f of x equals some algebra formula. Involving variable x. Right, that's what we did in that last example. We can describe a function, like I said, verbally. For example, I could say the function takes its input, multiplies by 3, then adds 1, then takes the square root of that. So this does define a function. And being able to go from the verbal to the algebra or from the algebra to the verbal is a useful thing. So just for shits and giggles here, an algebra representation of the function I just described verbally. You take your input, you multiply by 3. So your input is x. First thing you do is multiply by 3. Okay, that's 3x. Then you add 1. Okay, so that's 3x plus 1. And then we're taking the square root of all that. So that would be the square root of 3x plus 1. if I wanted to figure out how to take an output from this function and find the input from which it came, one way to do that is to think about the verbal description and then try to figure out how to undo each of these steps. And we will do that when we get to the end of chapter 4. That'll be a big thing for us. The two other ways to describe functions are definitely less exciting for us, but I could always give you a chart or table. Just explicitly listing inputs and outputs, right? So I have a column for inputs and a column for outputs. That only really works if your domain is finite. And like we've seen, we're working with the real numbers. Very rarely are our domains finite. Usually they have infinitely many numbers in them. So this is kind of a boring way to describe a function. But the last one is very interesting graphically. And this means, we're looking at the graph of the function. So, subset of the XY plane made up of input output pairs. All right, and you've seen this, like the parabola that you get when you graph y equals x squared. That is a total description of that function. Okay. I'm trying to think. So before I move on to talking about graphs, I want to take a particular function. I have a particular function in mind that I want to describe verbally and see if I can come up with an algebraic description. Turns out it's going to require something called piecewise functions. So before I move to the next example, I just want to define what a piecewise function is in case you haven't seen it before.
Excuse me, Professor.
Yes.
After XY, what did you write, please, for the number 4?
So this word is plane and then made up of input/output pairs.
Thank you.
Yeah. So in other words, the graph of a function is all the ordered pairs of the form a comma f of a, where the y coordinate is the output associated with the input a. All right. A piecewise function some people hyphenate piecewise, I don't. A piecewise function is one where the rule or formula for the output is different for different inputs. Right, so maybe if x is positive, I want to square x. And if x is negative, I want to multiply it by 3. That would be a valid way of defining a function. I could verbally define a function by saying, if you feed this function a positive input, it will square it, and that will give you the output. If you feed this function a negative input, it will multiply by 3, and that will be the output. But it's a different rule depending on whether the input is positive or negative. There are lots of other ways I could split up the input space, and the notation you usually see for this is something like this. So you see f of x equals, and then a big curly brace, kind of like the notation we use for sets, only there won't be one on the other side. And you'll have like, some formula here, and then some range of x values. So, and then the word if is often between these. And then some other formula here, and then the word if, and then some range of x values. Right, and there might be like 3 different formulas and 3 different range of x values. But that's the idea. So you want to compute f of some number. You would first check and see which group of x values does that fall into. If it falls into this first group of x values, then you would use this first formula. If it falls into the second group of x values, you would use the second formula. One of my favorite functions for kind of learning about piecewise functions is one that you guys encountered in your last homework set. So in your last homework set, whoa, sorry, my document camera just decided to turn itself on. All right, so what we're going to do is we're going to find a piecewise expression for a function that you encountered in your last homework set, the square root of x squared. Most of you saw it as the square root of 16x squared or square root of 9x squared, something like that. But let's see if we can find a nice piecewise expression for this. A nice piecewise expression for f of x equals the square root of x squared. I think most people came to a reasonable conclusion about this, but I got a lot of questions about it in email and on the Ask My Instructor thing. I know what everybody wants to say. Everybody wants to say that this is x, that the square and the square root cancel. And that's true, but only under certain conditions. So in order to do this, what I'm going to do is I'm going to start by making a little table. We're going to recognize a pattern, but instead of using the kind of notation you might be aware of already for this, I'm going to write it down piecewise, and we'll realize that the thing that you have a very good verbal description for also has a nice algebraic description. So let's start with like -3, -2, -1, 0, 1, 2, 3. All right. -3 squared. So I want the square root of -3 squared. That's the square root of 9, because -3 times -3 is 9. And the square root of 9 is 3. The square root of -2 squared, that's the square root of 4, which is 2. The square root of -1 squared is the square root of 1, which is 1. The square root of 0 squared is the square root of 0, which is definitely 0. The square root of 1 squared is the square root of 1, which is 1. The square root of 2 squared is the square root of 4, which is 2. And the square root of 3 squared is the square root of 9, which is 3, like it is above. So some input-output pairs, the input -3 gets sent to the output +3. The input -2 gets sent to the output +2. The input -1 gets sent to the output +1. The input 0 gets sent to the output 0. 1 goes to 1, 2 goes to 2, 3 goes to 3. So what is this? First, let's get the obvious out of the way. Everybody saw this as a part of, I think, 15C in the first homework set. Something very similar to it. What does this table make you think of?
Like a function?
Yeah, definitely. Maybe I should ask, if I had f of x equals x, would the table look like this, or would it look different? If this thing just simplified to x, would anything be different about these numbers? Specifically these numbers?
Yes. Still be negative.
Yeah, they would still be negative, but they're not.
So it's kind of absolute values.
Exactly. That's exactly what this is. So here's the deal. This looks like absolute value of x. And it is. That's exactly what it is. So there's that little mystery from the previous homework set solved, right? The square root of x squared, it's not x, or the square root of a squared is not a, it's the absolute value of x, or the absolute value of a. If the thing is positive, it gets left alone. If the thing is negative, it just gets turned positive, that's all. So I don't want to describe the absolute value function as the square root of x squared. That's kind of clunky. And these absolute value bars work. We all know what that means, but it's not a very nice formula, is it? Right? Like we're not immediately clear on how to manipulate this algebraically. Like what sort of things can I do with the absolute value function? The nicest way to do this is to describe it piecewise. So the absolute value function is actually a piecewise function. It does different things based on whether x is bigger than 0 or smaller than 0. If x is positive, or even equal to 0, then the absolute value function just returns that number, right? Like if you feed it 0, it leaves it alone. If you feed it 1, it leaves it alone, and so on. But what if x is negative? What algebra rule could I put here? What nice simple algebra rule could I put here that takes a negative number and makes it positive?
Times -1.
Yeah, that's it exactly. If you multiply a negative number by -1, you're going to make that negative number positive. So this is negative x if x is less than 0. And this is your definition of absolute value. So throughout this course and your calculus courses, anytime you see the absolute value function, you should think of this piecewise representation, right? In our heads, we have an idea of what absolute value is. It just makes the thing positive. But if you need to work with it in terms of algebra, if you need to, I don't know, graph it, or if you need to solve some equations involving the absolute value, then you need some sort of algebra definition that you can work with, and this is that. Okay. There are some much more exotic piecewise functions. I'd like to show you one other simple one before I show you the weird one. Compute, let's say, h of -2, h of -1, h of -1/2, h of 0, h of 3, h of pi, where the function I'm defining for you right now is called capital H, stands for Heaviside. Oliver Heaviside was a famous mathematician in the late 19th century, and this is called the Heaviside step function. And like the absolute value function, the kind of range of x values gets split up according to whether x is negative or non-negative. Very similar to this guy. But the outputs are different. In a very real way, this function is simpler than the absolute value function. So let's see if we can do these computations. These shouldn't be too hard. What is h of -2? If I want to compute h of -2, that means I want to plug -2 in here for x. In order to do that, because it's piecewise defined, I need to ask which one of these range of x values -2 lives in. So does -2 live in the first or in the second?
The first.
In the first, right? -2 is less than 0. So according to this rule, h of -2 is 0. All right, h of -1.
0.
Also 0, right? Because -1 lives in this collection of x values. H of -1/2.
Would be
Zero.
also 0.
Very good. What about h of 0?
1.
H of 0 is 1. Yeah, because 0 is greater than or equal to 0. 0 is not strictly less than 0. Okay. H of 3,
1.
also 1. H of pi,
1.
yeah, also 1, because pi is positive, right? Pi is like 3.1. Okay. I want to graph both of these functions for you and start looking at some other graphs. Technically, before I do that, I should define what a graph is. So leave some space here. We're going to come back and graph this thing. But in your notes, just for the sake of completeness, we do need to have the definition of a graph. There are some subtle questions that can be asked about graphs. So I'd like you to actually write this down. Remember, everything that goes on the .cam goes in your notes. The graph of a function, even if you already know what it is, please write it down. The graph of a function, let's say of the function, f, is the set of all ordered pairs of the form x, comma, f of x, where x runs over the domain of f. And we actually haven't defined the term domain for functions, but we've defined what domains are for expressions. I'll just remind you that the domain is the set of all the inputs for the function, and the range is the set of all the outputs for the function. Okay. Let's put that in here as I recall. The domain of the function f is the set of all allowable inputs or x values. And the range f is the set of all outputs for y values. Okay. And one way you can kind of think of a function, this doesn't have to do with graphs, but remember a function is a rule for pairing inputs and outputs. So you can kind of think of those things as being separate. F is just the rule that does the pairing, and this set over here is the domain. And the set over here is the range. That's a slight fib. The set on the right is actually called the codomain, but assuming that I'm only listing outputs here, it would also be the range. This is called a mapping diagram, by the way. And sometimes they'll be useful, like when we talk about composition. But graphs, we want to look at graphs for a minute, so let's do that. I'd like to go back and graph that Heaviside step function. I want to graph the absolute value function. And then one other kind of funky piecewise function before we look at a couple other things. Okay. So let's give ourselves an additional task here. Let's graph this. The horizontal axis is usually our input space. The vertical axis is our output space. And we would write y equals h of x or y equals f of x because the y values on the graph are the outputs. From the computations we did over here, I can plot a few points, right? The fact that h of -2 is 0 tells me that if I come out here, the point -2, 0 is on the graph. The fact that h of -1 equals 0 tells me that the point -1, 0 is on the graph. H of -1/2 equals 0 tells me that -1/2, 0 is on the graph. H of 0 itself is equal to 1. So that tells me that 0, 1 is a point on the graph. And I'll march out here 1, 2, 3. The next point I know for sure is on the graph is 3, 1. And then we also said pi, 1. Pi would be like just right next to this guy. And if you want to sketch the graph of this function in its entirety instead of just a few points, you just observe that it's a constant function. If x is less than 0, it's equal to the constant function 0. So the whole graph over here looks like this. And if x is greater than or equal to 0, it's the constant function 1, like the line y equals 1, which is a horizontal line looking like this. There's a bit of an interesting question about what happens at x equals 0 itself. Well, we know when x is equal to 0, h of 0 is 1. But as you sneak up on 0 from the left, we do stay down here. And so we would describe that with like an open circle there. So this is the graph of the Heaviside step function. And you can see why we call it a step function. It's because of the graph. This is like a stair, right? It's like a little stair step. You're starting down here at 0, and then at 0, you take a step up to 1. This is a really important function in differential equations and signal processing. If you want to describe like turning on a switch at time t equals 0, or you want to describe like kicking a physical system, like you've got something hanging from a spring and you want to hit it with a force of 1 at a certain time, this function is precisely how you would do that. So very important to electrical engineers, dynamical systems people, physics people, and so on. Heaviside step function has a graph that looks like a step. Oliver Heaviside was a very interesting guy. Let's graph the absolute value function. I'm pretty sure you've done that before, but I'll be able to show you a little bit more how one generally graphs piecewise functions by using that as an example. So we'll think of this as a separate example graph. The absolute value of x. X, yeah. X greater than or equal to 0, and negative x if x is less than 0. Okay. Generally, the way you graph piecewise functions, you start off by totally ignoring this stuff. You just look at these two different formulas. Draw the graph of each of those on their own. And then you're going to like erase part of it and stitch those two graphs together. So in what follows, I am going to assume that you know how to graph lines. Obviously, everybody here has had some amount of algebra in the past. So to graph this, we're going to start by sketching two graphs. Y equals x and y equals negative x. All right. So here's my x-axis and my y-axis for that first one. We all know that y equals x is a line with slope 1 passing through the origin. So it goes through 0, 0, it goes through 1, 1, it goes through -1, -1. All right, here's the line y equals x. And the line y equals -x is a line through the origin with slope -1. Looks like this. All right, he goes through 1, -1, -1, -1, +1, and the origin. And if you want, you got 3 points there. So to graph a piecewise function, in general, you graph each of the pieces, right? This is like one of the pieces, y equals x, and this is like one of the other pieces, y equals -x. Then what you do is you look at the restrictions and you throw away the part of this graph that doesn't match this restriction. So let me use some color here. For this part, if x is greater than or equal to 0, so I want to look on the graph of y equals x and then discern which piece has x greater than or equal to 0. Well, here's my x-axis. The x's which are greater than or equal to 0 are all of these guys, everything to the right. Of the origin. So that corresponds to this part of the graph. On the other hand, the x's which are less than 0 that's everything to the left of the origin, not including the origin itself. I don't know if the difference between the light blue and the dark blue is really going to materialize here, but I'm trying. So what we're going to do is we're going to take the shaded part of each graph, this part from the first and this part from the second, and set them on top of each other. And that will be the graph of my absolute value function. So from the y equals -x graph, I take just this part. Now from the y equals +x graph, I take just that part. Technically, the point at the origin is coming from the y equals +x graph, but it really could come from either since they both go through the origin. So this is the graph of the absolute value function, which you've probably seen before. But that's how you graph piecewise functions in general. You graph each of the pieces, and then you just hold on to the portion of each graph that is specified by the restrictions on x. So from the y equals x graph, I just held on to the stuff where x is greater than or equal to 0. That's this stuff. I'm forgetting all about this stuff. I don't care about this because the x values here are not greater than or equal to 0. From the y equals -x graph, I just hold on to the portions of the graph where the x values are negative, which is this stuff. And I don't care about this because none of these x values are less than 0. All of those x values are greater than 0. And then I take this guy and I copy and paste him here. I take this guy and I copy and paste him here. And that is how you get your graph of a piecewise function. So graph each of the pieces, identify the part of the graph you want to hold on to, and then copy and paste those on top of each other. this is kind of the simplest example I can come up with. We're going to look at some more complicated ones in a second. Are there any questions about what we've done here? Yeah, I see something in the chat. How would it be with all the lines facing down? I'm not entirely sure I understand the question there. Could I ask for a little more specificity? You mean like if both lines had a negative slope, or what do we mean? Or so if this was flipped over vertically, there's a few ways we could get a graph like that as a piecewise function. One of them would be to negate both of these. If you make this negative x and this positive x, then you would be holding onto this piece from the first graph and this piece from the second graph, and that would give you a kind of downwards opening V. Another way would be to just negate everything here, right? You could just say, I'm going to look at the negative absolute value of x, and we'll see a little bit later that multiplying a function on the outside by -1 flips it over vertically. A third way we could get that is by switching these restrictions. If I put x is less than 0 here, and I put x is greater than or equal to 0 here, that would, again, hold on to this piece from the one and this piece from the other, which would have that same effect. But let's look at something even weirder. Let's look at a piecewise function where the graph pieces are not necessarily straight lines. So maybe, well, let's see. I guess I'm not allowed to assume that you guys are super comfy with quadratics, but let's do it anyway, because I know you are. And then after this, I've got a really weird one for you. Okay, so let's sketch graph. I'll call it g of x. And we'll define it piecewise to be x squared if x is less than 0, and 1 minus x if x is greater than or equal to 0. We don't have to make these splits at 0, right? These restrictions on x can be all sorts of different things, but just without thinking too hard, this is something that comes to mind. The graph y equals x squared is a parabola, and the graph y equals 1 minus x is a straight line. And we're going to begin with the graphs of those pieces. So even if you forgot what y equals x squared looks like, we can get through this. I'll give us that. Parabolic. It looks like this. 0, 0 is on the graph. -1, 1 is on the graph. +1, 1 is on that graph. Also, you have things like 2, 4. And -2, 4. So there's the graph y equals x squared. The graph y equals 1 minus x. That's the same as -x plus 1. So that's a line with y-intercept 1 and slope -1. Like this. Now I'm going to look at the restrictions. So if x is less than 0, that means I'm looking at all the stuff to the left of the origin here. It means I'm looking at this portion of my parabola. Not including the point at 0, 0. Because there x is exactly equal to 0. And when x is exactly equal to 0, I should be using the other piece. So here I'll scroll down. Here are all of the x's which are greater than or equal to 0. And so the corresponding portion of that graph would be this part. And if I take those two and overlay them, just copy and paste the shaded part from each. Down here, something that looks like this from the first. And something that looks like this from the second. So here's the graph of G. Oh. Any questions about where the black graph at the bottom here is coming from? How we got that from these? Mostly feeling good? Okay. One last piecewise function to bake your noodle a little bit. This one also has a funny name. We'll call it capital D of X. D here stands for the name Dirichlet, or Dirichlet if you claim him as a German, but most people claim him as a Frenchman. This is equal to 0 if X is rational, equal to 1 if, actually, X is not rational. Yeah, indicator for rations. 1 if X is rational. I'll remind you some notation. We talked about this early, but this means X is a rational number. This would be read as X is an element of Q, and remember Q is the symbol we use to refer to the collection of all rational numbers. And this statement would be that X is not rational, i.e. X is irrational. Okay, so what does this function do? Let's evaluate it at some inputs and see what outputs we get. Okay. So here are just some values we can compute. This is going to go real fast. What is d of -2?
Would it be 1?
Yeah, d of -2 is 1 because -2 is a rational number, right? -2 can be written as -2/1, both of which are integers. Okay, don't think too hard. What's d of -1?
1.
d of -3/2?
1 again.
d of -1/3?
1.
d of 0?
1.
1, d of 1, also 1, d of 3/4, also 1. Right, all of those numbers, -2, 1, -3/2, -1/3, 0, 1, and 3/4 are all rational numbers. Okay. What's the square root of 2?
0.
0, because the square root of 2 is irrational. The 1 over the square root of 2 is also 0. The pi is also 0. The negative square root of 3 is 0. Right? You get the idea. What this function does is if you feed it a rational number as its input, it spits out 1. And if you feed it an irrational number as its input, it spits out 0. Functions like these are called indicator functions. They're not going to play a huge role in our course, but they do make for interesting examples. And the graph of this function is frankly very weird. All right. I'm not going to plot every ordered pair here, but let's do like 1, 2, positive 1, positive 2. Certainly, d of negative 2 is 0. Sorry, d of negative 2 is 1, d of negative 1 is 1, d of 1 is 1, d of 2 is 1. What else did we do? Negative 1/3. D of negative 1/3 is definitely 1. D of 3/4 is 3/4. That's also 1. And what you start to see is you've got a lot of things up here. At every x value, which is a rational number, you get a point up here along the line y equals 1. If we tried to break this down into pieces, your first piece would be the line y equals 0. Your other piece would be the line y equals 1. Those are both horizontal lines. But it's not split up over intervals. It's split up over whether you are irrational or rational, which are not connected sets. Between any two rational numbers, there's infinitely many irrationals. And between any two irrational numbers, there's infinitely many rationals. So this function is jumping back and forth between 0 and 1 all the fucking time. And the truth is, there's a lot more numbers down here. There's a lot more points on the graph down here than there are up there. This is hinting at a very weird reality of the real number system that we talked about a little bit on the first day, and that's that the irrational numbers they're both infinite sets. There's infinitely many rational numbers and there's infinitely many irrational numbers, but somehow there's more irrationals than there are rationals, and that's just a weird fact. So what do we say? Square root of 2, that's like 1.4, so that's definitely an entry down here. 1 over the square root of 2, it's like over here. And there's lots and lots and lots more. Pi would be like out here. So this is what the graph of the Dirichlet function looks like. It's kind of like a faint sprinkling of dust up here along the line y equals 1, and a much heavier sprinkling of dust down here along the line y equals 0. But still you can kind of see the two pieces of the piecewise function, right? The line y equals 1 and the line y equals 0 are the two pieces that make this up. They're just split up in a much weirder way than like this example. Okay. I think that's enough on graphing piecewise functions. What would you like to, let me take a look at your homework and make sure I'm not, I feel like I jumped over something. Well, no, maybe we're just about right on time. Maybe this is okay. Oh yeah. We should play a few of those games. Look at some of this. We can do a little more of that. Good for us. And yeah, two things I want to talk about still in these last few minutes. The first thing I want to talk about here at the end is something called net change. And we gotta have a definition. So the net change of a function f from, you gotta specify two inputs from x equals a to x equals b. is by definition the difference f of b minus f of a. And the way you can think about this is just how, from as x goes from a to b, as you move sideways, how far does the graph move up or down? It's kind of like slope. We'll connect this to something that is literally slope in the next class. We do a few net change calculations here, and then some kind of qualitative analysis. Oh, let's okay. And I'll just make up some distances for these. Let's call this 4. Let's call this 1. Let's call this. It's not quite perfect, but then, okay. And let's call this over here 6. Let's actually specify some y values. One and call this. Okay. So we have some points here on this graph. And I can ask some sort of silly questions about it and some less silly questions about it. First, let's find the net change explicitly from, let's say, x equals 0 to x equals 1. X equals 1 to x equals 6. And then let's answer, this guy is the net change from x equals 1 to x equals 4. Negative 0 or positive. And then C, let's answer that same question as B, but from x equals 2 to x equals 6. All right, so we got a few things to do here. First, maybe just ask a silly question. What is f of 4? See how comfy we are with just the definition of the graph. What is f of 4?
3.
Would it be 3?
Very good. F of 4 is 3. All right. So if you want to find f of something, right, you look at that thing on the x-axis, you go up to the graph, and then you ask yourself, what's the y value there? Similarly, f of 1 would be 3. F of 2, I don't know exactly what that is because we haven't labeled it, but I know it's bigger than 3. What is f of 0?
1.
Very good. F of 0 is 1. And so is f of 6. All right. So if I'm going to find the net change from x equals 0 to x equals 1, this thing, this is going to be f of 1 minus f of 0. Right? That's the definition. It's just f of b minus f of a. f of 1, we said is 3. So that's 3 minus. Then f of 0, we said is 1. So the net change from x equals 0 to x equals 1 for this function is 3 minus 1, or 2. The net change from x equals 1 to x equals 6 is f of 6 minus f of 1. And it might feel silly to do this, like this step where you're writing it out, the definition, without plugging in, but you really want to do this. Okay, later in the course, I'll refer to this as kind of setting up the problem or setting up a schematic for the problem. It's a really wise thing to do. Yeah, if you gotta go, you gotta go, that's okay. So by writing this out, we can kind of pause, let the paper remember for us what it is we're doing. We don't have to hold it all in our head. And you can imagine if this was more complicated, you'd really want that. You don't want to have to hold the whole problem in your head. So just write down one step at a time. All right, f of 6, that's 1. Minus f of 1, that's 3. It's 1 minus 3, which is negative 2. Why was the first net change positive and the second net change negative? Why did this one come out to positive? This one come out to negative? Can we give an answer to that question in terms of the picture?
Because the y values are different. One's bigger than the other.
That's true. That's true. Specifically, let's look at the first guy, the 0 to 1 guy. If we look here, overall, as x goes from 0 to 1, the graph went up, right? We finished higher than we started. That's why this guy is positive. Overall, we've gone up. You'd say our net change is positive, right? Like at the end of the month, if I have more money in my account than I did at the start of the month, I would say my net value has gone up. The net change for my account has gone up because it ended higher than it started. Similarly, the second guy is negative because as x goes from 1 all the way out here to 6, we've overall gone down, right? At 1, we're up here. At 6, we're down here. So since this is lower than this, that net change is going to be negative. We always read from left to right. So with that in mind, is the net change from 1 to 4 going to be positive, negative, or 0?
Will it be 0?
Good, it's going to be 0 because I'm ending up at the same height I started at, right? If at the end of the month I have the same amount of money I did at the start of the month, then the net change in my account is nothing. I'm ending at the same place I started. So this one would be 0. Okay, and what about from 2 to 6?
Negative?
Negative. And you see, even though I don't know what f of 2 is, this is sort of the power of thinking about things in this way, even though I can't compute the net change because I don't know what this y value over here is, the graph just doesn't have it labeled, I can still say that that net change is going to be negative because the y value over here at 2, the output, is larger than the y value over here at 6, which means that as x went from 2 to 6, overall, my function has gone down. My outputs have decreased. So this one would be negative. Can anybody identify another interval, another a and b, where the net change would be 0?
One and 6.
Almost. 1 is up here, which is above 6.
0 and 6.
0 and 6?
0 and 6.
Very good. So we could ask, find another interval on which the net change would be equal to 0, and from this point to this point, right? That's what works. And I'm pretty sure everybody could interpret that question and find the points. But remember, when you're describing function behavior, we always do it in terms of the input. And that is why that rule saying every input goes to 1 and only one output is so important. If I tell you, look at the graph where x is equal to 0, there's only this one point. There is no other point above or below that you could confuse it for. So when I say, look at the graph when x is equal to 0, you know I'm talking about this point. When I say look at the graph for x is equal to 6, you know I'm talking about this point and only this point. So yeah, from 0 to 6. Now, the truth is, looking at that graph, there's actually lots of others, right? Take any horizontal line, like right here, and it's hitting that graph in 2 places. So like this point and this point, but I don't know exactly what those x values are. It's not clear. So the other one that's obvious is 0 to 6. Okay, that is net change. And I think that is where we're going to wrap up for today, because yeah, we're a little bit over time. All right, so I'm going to end it here today. Please knock out that homework set. It is due at the start of class on Thursday, remember. So you don't have a full week, you just have a couple days. You need to get in there and start on it today. On Thursday, we're going to talk more about graphs of functions. I'm going to show you how to graph lots of other things. And please be mindful that as you work through that homework, the graphing problems, you need to draw the graphs by hand. If you don't draw the graphs by hand, you're wasting your time. If you're having a hard time remembering what some of the basic graphs look like, come over here to the modules. I do have a resource for you, and we'll use this more later in the term. Graphs of parent functions, these are like the basic functions whose graphs you should know. So if you forget what the graph of y equals x cubed looks like, just come over here and click this, and there you go, there's the graph of x cubed. Or if you forget what the graph of the cube root of x to the 1/3, here's that. So you can use this Desmos resource as much as you want. Please do try to get these graphs in your head nice and clear. These are all kind of basic graphs that we're going to use to build more complicated things in the future. You need to know what 1 over x squared looks like, or what 1 over x looks like. It's all right there. Okay, that's it from me. Please work on that homework set. If you get stuck on anything, you can come see me in office hours or send me a Canvas message or post to Discord. That's it. I'll see you all on Thursday.